Okay, so we will come back to this again, that continuing with this problem. Just before beginning this, let me tell you one thing, that for the DC circuits we are trying to see so many different type of problems, but at the same time when we will come to the AC circuits, right, at that time number of examples I have to reduce, because at that time complex number will be involved, and it computation it will take much more time, right? It will consume more time to solve such things. But basic idea for DC circuit, whatever circuit laws and theorems we are learning, it is same for your AC circuit, apart from your maximum power transfer theorem, that we will see later, right. So just come to another problem, right. So in this case, so what you can do is that you determine your for this problem you have to determine I1 and I2 using mesh analysis of the circuit shown in this figure, right. So this is the figure, and just this thing, and your in this case that you have one 50 volt source, right, and one your 10 volt source. So the 10 volt source, and let me clear it, let me clean it first, right. So we have one 10 volt source and we have one 50 volt source, and you have I1, I2, and this is a dependent voltage source, and here it is 30 I1 and here it is your I2, right, and you have to solve for I1 and I2. So same as before, if you write your KVL equations for this one, later it is written. So basically if you move like this, for this is mesh 1 and this is mesh 2. So if you move like this, so easily you can write down your what you call that your KVL equation. For example, in mesh 1 if I apply, so I am moving like this clockwise, we are moving like this. So it will be first minus 50, right, then plus 10 I1, right, plus 20 I1, right, and here we are moving in the direction I1 and this is your I2, right. So resultant in this direction is I1 minus I2, so plus 10 I1 minus I2, and encountering and moving this loop, so minus terminal first, so minus 30 I1 is equal to 0. So this will be your one equation, right. Later it is given, but this is one equation. So let me clear it. So similarly, when you apply your KVL in mesh 2, right, same way you can do it. For example, I am moving from, say, starting from this 5 ohm resistance. So it is 5 I2, then encountering plus 10 volt, plus terminal first, plus 10, right. Then here also if you move like this, so plus 30 I1 is coming, so plus 30 I1, right, and we are moving in this direction, this is I2 and here I1 is there. So in the upward direction is I2 minus I1, so plus 10 I2 minus I1 is equal to 0, right. When I am writing such equations, this is plus, right. When I am writing such equation, hope I am not missing anything, right. So two equations you will get, and accordingly from that you have to solve for I1 and I2, right. And there let me clean it. So if you go to this for mesh 1, this is the equation, finally it is coming I1 minus I2 is equal to 5, right, and for mesh 2 it is your coming your this thing your 4 I1 plus 3 I2 is equal to, this is for mesh 1, this is for mesh 1, I1 minus I2 is equal to 5, right, and this is for your mesh 2, that is your 4 I1 plus 3 I2 is equal to minus 2. If you solve it, you will get I1 is equal to 13 by 7 ampere and I2 is equal to minus 22 by 7 ampere, right. Next one is they determine the power dissipated by the 4 ohm resistor in the, it is actually, hold on, actually it is just hold on, it is in the circuit, right, of figure 3 your figure 3.27. So what is the power supplied by the 30 volt source, right. So your if you just let me clear it. And if you just look into this, in this circuit, that you have the one dependent voltage source 10 V1, this dependent voltage source is there 10 V1, and this V1 actually this is the voltage, right. And one thing is there, so look, whenever we are drawing circuit, if I show arrow upward, I mean arrow like this, and the arrow is always plus and nothing is marked, mean this is minus, right. This way you have to assume whenever we will put arrow. So here arrow is there and this is minus, that means this point you take plus and this is your minus, right. Even if it is not mentioned, but any if it is arrow here and nothing is here, means this is plus, this is minus. And this 10 V1 means this V1 actually this is the voltage, this is the V1, and this is a dependent voltage source is given something like this 10 V1, right. So if it is so, then first what you do is you find out an expression of I1 in terms of V1. Earlier we have seen that how to find out. So what you can do is that first take KVL like this, you take KVL here. So in this case what will happen, not going like this the way it is shown, I have shown it here, but go like this. Then in this case what will happen, this I1, so it will be actually, if you just putting it here, taking V1 together, right, then what will happen, that you write 5 I1 and this terminal, this point is plus, I marked it here, right, plus V1, right, and encountering minus terminal here. So minus 30 is equal to 0, right. That means my I1 will be equal to 30 minus V1 divided by 5, right, because we have to obtain first I1 in terms of V1, right. Or in other way I can make that your V1, this is I1, or other way here I am writing V1 is equal to your 30 minus 5 I1. I think this is required for our this thing, 30 minus 5 I1, right, that is your V1. So V1 you have to obtain in terms of I1, because we have to solve for I1 and I2 first, right. So V1 is equal, from this it is clear that I applied that KVL here only, that is your 5 I1 plus V1 minus 30 is equal to 0, right. This is required, because before going to those equations, first trying to let us make all these things clear, or what you call clarification here itself, right. So now I am clearing it, right. So once it is done, then what you do, that's why first I am writing 5 I1 plus V1 minus 30. So V1 is equal to 30 minus 5 I showed you. Now you apply your what you call that KVL in mesh 1. So if you do so, if you write KVL here, look how we are writing. If you write KVL here, so it is actually your 5 I1, right. I am writing here. Later it is written 5 I1 plus, it is also 10 I1, that is it is 5 and 10 are in series, right. So basically 15 I1, so plus 10 I1, then plus this current is I1 this direction and I2 is going this direction. So it is 1 into I1 minus I2, right. Then minus 10 V1, then here it is minus 30 is equal to 0. This will be your what you call that your if you apply KVL in this mesh. Similarly, if you apply your what you call KVL in mesh 2, so let me clear it. If you apply KVL in mesh 2, so same way you can move. So in this case it will be starting from here. If you move like this, starting from here, so it is 4 I2, right. You come like this plus 10 V1, right. V1 expression you got in terms of I1 and going upward. So 1 into, and this is your I1, because current is I1 moving like this. So I2 minus I1, right. Hope I have not missed anything, is equal to 0, right. This is your second equation. So let us clear it, right. So if we move like this, so this way mesh 1 will get this equation. Mesh 1, for mesh 1, if you write, I wrote it for you. So, this is the equation, right. I wrote something after simplification is like this. So, this is equation 2 say, and here you have to substitute V 1 is equal to that V 1 is equal to your 30 minus 5 I 1, there you substitute such that you will get an equation in terms of I 1 and I 2, right. Similarly, let me clear it. Similarly, if you go to your if you go to for mesh 2, I wrote for you that this is also this mesh 2 KVL you apply, and finally here also you put V 1 is equal to 30 minus 5 1. So, another equation you will get 51 minus I 1 minus 5 I 2 is equal to 300, and solve this to that equation 3 and 4 you solve it, right. If you solve it, so you will get I 1 is equal to 4.84 ampere and I 2 is equal to minus 10.64 ampere, and power dissipated by the 4 ohm resistor is minus 10.64 square into 4. So, 453.25 watt, and power supplied by the 30 volt source, it is 30 into 4.84. So, 145.2 watt, because from the source that I 1 source supplying I 1 current. So, it is 30 into 4.8, basically it is 30 volt into I 1 is 4.84. So, 145.2 watt, right. So, next take this simple example. So, determine I 2 in the circuit shown in figure this 3.2. So, this is the circuit, you have to find out your I 2. Look, this current actually, this current 5 ampere is this direction it is there, right, but we have taken your this way we have taken, right. That means I 1 actually is equal to minus 5 ampere, because when you move I 1 like this, I 1 is going like this I 1, right, going like this clockwise, and this is coming out. So, just opposite direction. So, I 1 is equal to minus 5, that nothing else, that is all. After that you apply your what you call KVL in this mesh. So, if you move like this, so I move like this, I move like this, so it will be minus 100. Now, no need to repeat again and again, now you have understood. So, minus 100 plus 10, right, into your this is the current I 2, this direction this is the current I 2, and I 1 is in this direction. So, it will be 10 into I 2 minus I 1, right, plus 5 into I 2, because this 5 ohm resistance is there, this 5 I 2 is equal to 0, but I 1 is equal to minus 5 ampere. If you substitute I 1 is equal to minus 5, then it will become minus 100 plus 10 into I 2 plus 5 I 2 is equal to 0, from which you have to compute I 2. So, the calculations it is given here, right. So, this is a simple thing. So, I 2 is equal to actually 10 by 3 ampere, right, this is the answer. So, similarly, for this one, determine I 1, I 2 and I 3 of the circuit shown in figure this, right. So, in this case, if you look into that, for this problem you have to find out your I 1, then I 2 and I 3, right. And if you look into that this is mesh and this is one mesh, and in between two mesh one current source is there, right. So, accordingly you have to see that this is creating a super mesh, right, because this is mesh and these two mesh in between one current source is there. So, it is computing, it is giving you super mesh. So, and if you look into that, this current we are taking actually this way if you take the loop, it is I 2, and this way we are taking, this direction is I 1, and 5 ampere shown it is upwards, right. So, now from that we have to see that how we can solve this one, that because this is creating a super mesh. So, what we can do is first, and because of that some constant equation will come. So, how one can do is, look, because it is a super mesh, so one constant equation will be there. So, let me clear it first. So, before writing the KVL, so this is one node is there, node A, right. So, this I 2 current is coming. So, this is actually your I 2, because we are moving clockwise, this is I 2, right, and this is your 5 ampere current going upwards, and this actually I 1 goes like this is I 1. So, this is I 1, right. So, if you look into that, therefore, this I 2 current entering at node A. So, and 5 ampere and I 1 both are leaving. So, I2 is equal to actually 5 plus I1, right, or I2 minus I1 is equal to 5 ampere, right. This is one way. Easily you can apply your what you call that your KCL at node A. Another thing is simple thing. Another thing is this I2 is moving this way, and this I1 is moving this way. This is your I1, and this 5 ampere direction is upward. So, upward direction current is actually I2 minus I1, this I2 and minus I1, right. So, and this is upward 5 ampere, that is also directly you can write 5 ampere the way you want, right. So, let me clear it. The equation we will see later. First we have to understand, and this as this is creating a super mesh. That means what we have, what basically you have to do, you have to apply KVL like this, right, because this you can exclude and then make a dashed line, and the way I showed, and you can do it. So, that we have gone there, right. So, let me clear it. So, for this is a super mesh, I told you. So, write down those, easily you can write down the equation. It will be, now from my mouth I am telling, you can understand, it will be, if I move like this, it will be 2 into I1 minus I3, because this is your resultant in this direction, sorry. So, just hold on. So, resultant is in this direction, right. So, it is your I1 minus I3, here it will be your I2 minus your I3, right. So, 2 into I1 minus I3 plus 4 into your I2 minus I3 plus 10, and if you come like this, plus your I1 into 1 is equal to 0, right. So, let me clear it. So, if this way, similarly for the other this mesh 3 you can apply, mesh 3 also you can apply KVL. So, if you apply this KVL, so your in the super mesh, so this is the equation I wrote for you, right, and if you for mesh 3 you apply KVL again, this is your equation, this is for mesh super mesh 1, the equation 1, and for mesh 3 equation 2. So, apply KCL at node A. I told you earlier that I2 minus I1 is equal to 5, this is equation 3, right. If solve equation 1, 2 and 3, so you will get your I1 is equal to minus 100 upon 18 ampere, I2 is equal to minus 10 upon 18 ampere, and I3 is equal to minus 80 upon 54 ampere. So, this is the answer, right. So, one thing I can give you as an exercise, say you also find out what is the power your supplied or absorbed by this current and the voltage source. This is not done here, but is an exercise for you. You please do it. Next is that your nodal versus mesh analysis. So, where you will go for nodal analysis and where you will go for mesh analysis. Look, this is actually generally both nodal and mesh analysis provide a systematic way of analyzing a complex circuit, right. So, if you have, for example, just hold on, for example, a network, right, a network that contains many series connected elements, right, super meshes or voltage sources are suitable for mesh analysis, right. And similarly, a network that contains parallel connected elements, current sources or super nodes are suitable for nodal analysis, right. But this is actually something we are giving. Actually, question is that you have to see that where you have a minimum number of equations. If you see that your for nodal analysis, if you have a minimum number of equations, because a minimum number equation means your computation time is less, right. So, you have to see that whether nodal analysis or mesh analysis, which one will be suitable, such that you have a minimum number of equations. That is the idea for your what you call for nodal or mesh analysis, right. So, ultimate thing is, if voltage are required, then you go for nodal analysis. If currents are required, better you go for mesh analysis, but both the cases you please see that whether you need for nodal analysis where you have a minimum number of equations, right. This is the idea. So, this is the difference between nodal or what you call mesh analysis. Now, some exercise you will do at least 10 problems I am giving you. So, here you have to find out V1 and V2, right, using nodal method, answers are given everywhere. Right hand side you see V1 is equal to minus 2 volt and V2 is equal to minus 14 volt. This will do. Similarly, you take example 2. So, using node voltage method, determine V1 and V2 of the circuit shown in figure 32. It is chapter 3, 3.32. So, figure 32. So, this is another one. This will solve. Then another one, the figure 3.3, using nodal analysis, find the power delivered by each source in the circuit shown in figure your 33. So, this is the figure, right. So, you have to find out the power delivered by each source of this circuit, right. Next, these answers are given 150 watt, 80 watt and 144 watt respectively. Answers are given. So, determine V1 and V2 of the circuit shown in figure your 34. So, here also V1 and V2 you have to find out, right. Answers are given. Hope all answers are correct, but I suggest if you find any error of this thing, you please let me know so that I can rectify myself, right. So, as example 5, you have to find out V1, V2 and V3 and I of the circuit shown in figure 35. So, this is the 35 figure. You have to find out V1, your V2, here I am asking V1, V2, V3 and I V3, V2 is here. Hold on, V2, don't overlook this. This is actually V2, right. Here it is given V2. You have to find out V1, V2 and V3, right, and I, this I for this problem, right. So, let me clear it. Here something different, because generally we are marking top, but here it is given. You find out answers are given V1, but note that V2 is not your reference node, that 0 potential nothing. V2 is equal to minus 72.73 volt. Answers are given. Then example 6, using nodal analysis, you have to determine Ix, right, of the circuit. So, Ix, it is a dependent voltage source is there. Answer is given Ix is equal to 2.31 ampere. Similarly, for problem 7, that example 7, find by using mesh current technique, find I, actually it should be Ix, right. That is a nodal analysis, actually this should be your Ix, right. So, here it is a correction, this is should be suffix is Ix, right. Find Ix. So, same figure, that figure 36 means this figure, same figure, and you have to find out, and this is also your Ix, right. So, Ix, because it is also 2.3, answer has to be same. So, 2.3 ampere. So, this is a correction only, right. So, this will do it. So, let me clear it, right. So, this is you are asking for your nodal analysis, and same thing is asking for mesh analysis, right, both you will do. Then 3.8, you have to find out V1, V2, V3 of the circuit shown in figure this. So, you have V1, V2, V3 all are marked. So, and a dependent and independent your this thing, a 4 Ix, that is your 10 ampere thing is there, and a 4 Ix your dependent current source is there, right. So, just you all answers are given, right. So, another thing is, just hold on, so is okay. And another thing is that your problem 3.9, using mesh analysis you determine Ix of the circuit, right. So, there is a dependent voltage source is there and this current is Ix. So, you find out this one, and answer is given Ix is equal to minus 5 ampere, it is given. And last problem, I actually have many problems, but only this 10 I am giving. For DC circuit only, AC circuit problem will be reduced. So, using mesh current method, determine power delivered to the 2 ohm resistor in the circuit. So, this is your what you call that your last problem, problem 10. So, you have to, using mesh current method, you have to determine that power delivered to the 2 ohm resistor in the circuit shown in figure this. So, this is that figure, right. So, 2 independent your voltage sources are there, 1 dependent your current source is there, right. So, all your all these things, I think here one just hold on, I think here one this one your sorry, here it is a dependent current source, right, because this Ix here you change this thing, that it should be your 4 Ix, right. So, this is a correction, right. So, anyway, so with this your this chapter will be closed. So, we will go to the next one, right. So, hope detail have been made, so many examples have been solved, and I do believe that you have you have understood all these things, right. So, next one will be your circuit theorems, right. So, circuit theorems, actually in chapter 3 we have seen that sometimes we have used KCL and KVL, right, and circuit analysis, you are tampering with its original your what you call without tampering its original configuration, right. But in major drawback of this circuit, you have this analysis, your KCL, KVL, then you are going for nodal and mesh analysis, right. You have to this thing you have to solve a very large complex circuit, right. So, over the years, and it is a tedious computation is involved. So, to handle the complexity of the circuit over the years, the engineers have developed some circuit theorems, right. And so, such theorems are called sometimes Thevenin's theorem and Norton's theorem, right. So, these theorems are applicable to linear circuit, and in this chapter, right, we first discuss the concept of circuit linearity, and also we will discuss the concept of superposition, source transformation and maximum power transfer. I have underlined those things. So, here circuit theorem we will learn Thevenin's theorem and Norton's theorem. Apart from that, we will learn superposition theorem, then your source transformation and the maximum power transfer condition, right, for the DC circuit first. So, whenever we go for linearity property, so basically it is the property of an element describing a linear relationship between cause and effect. This you know even from your higher secondary physics, this you know that it is a property of an element describing a linear relationship between cause and effect, right. So, although linear property applies to many circuit elements, right, but in this chapter we will restrict it to the resistors only, because we are handling only DC circuit. So, the linearity property is a combination of both the homogeneity property, that is your scaling, the homogeneity property, that is the scaling, and the additivity property, right. So, one is homogeneity, another is additivity, right. So, this linearity property is a combination of both. So, just let me clear it, right. So, homogeneity property, it requires that if the input, it is called excitation, if the input your called excitation, here it is just you mark this one, if the input is excitation and is multiplied by a constant, then output is also multiplied by the same constant. For example, when you make V is equal to IR, say in Ohm's law, right, then if you multiply it by constant K, may increase, may decrease. So, KV is equal to KIR. So, we will come to that. Thank you. We will again come to that.